Somewhere past the edge of the solar system, a machine older than most of the people reading this went quiet. Not dead, not destroyed. Quiet. In the way that a person goes quiet right before you realize something is deeply wrong. For nearly 5 months, the most distant object humanity has ever built kept talking to Earth, and every single word coming out of its mouth was gibberish. Engineers at NASA's Jet Propulsion Laboratory sat in front of screens filled with static, watching a spacecraft that had survived nearly 50 years in the vacuum of interstellar space slowly slip toward something they had never had to plan for. Total, permanent silence. And here's the part almost nobody talks about. This wasn't a movie. There was no backup system waiting in the wings. If they failed, that was it. Forever. This is the story of Voyager 1's near-death experience in 2023 and 2024, and what it reveals about how fragile our grip on deep space actually is. Let's set the stage, because the scale of this thing is almost impossible to hold in your head. Voyager 1 launched in 1977, back when the idea of a computer fitting in your pocket sounded like science fiction. It flew past Jupiter, past Saturn, and then just kept going, past the orbit of Pluto, past the heliosphere, past the last measurable. Trace of our sun's influence until in 2012, it became the first human-made object to cross into interstellar space. Today, it sits more than 15 billion miles from Earth, so far away that a radio signal traveling at the speed of light takes over 22 hours just to reach it. Send a command, and you wait nearly 2 full days for any kind of reply. Every conversation with Voyager 1 happens in extreme slow motion, across a gap so vast that light itself feels sluggish crossing it. Now think about what that distance actually means when something breaks. On Earth, if your laptop crashes, you restart it, maybe you call tech support, maybe you take it to a shop. None of that exists out here. There is no shop. There's no technician who can put their hands on the machine. There's only code, sent across a gap of light hours, hoping it lands correctly on hardware that hasn't been touched by human fingers since the Ford administration. And in November 2023, that hardware started failing. The failure hit something called the Flight Data Subsystem, the FDS for short. Think of the FDS as Voyager's translator. Every scientific reading, every engineering status update, every scrap of information the spacecraft gathers gets packaged by this one system before it's transmitted home. Without it, Voyager isn't mute. It's actually worse than mute. It kept transmitting a steady signal, precisely on schedule, exactly as it always had. But the content of that signal was nonsense, a repeating pattern of ones and zeros that meant nothing to anyone. Imagine calling someone you love, hearing them pick up, hearing them breathing on the other end, and every word that comes out of their mouth is scrambled static. That's what NASA was listening to for months. And here's where it gets worse. Voyager 1 doesn't have a backup FDS. There was no redundant system to switch over to, no failover, no plan B baked into the hardware. If the team couldn't diagnose and repair this fault, the mission was over. Not delayed, not paused. Over. After 46 years of exploration, after outliving the careers of the engineers who built it, after becoming the single farthest traveled artifact of human civilization, Voyager 1 was one unsolved bug away from becoming permanently unreachable space debris, forever drifting, forever silent, forever alone. Read that again. One chip, one unfixable fault, and decades of irreplaceable science gone. So what do you do when the patient is 15 billion miles away, and every message you send takes almost 2 days to even arrive? You don't panic. You think. The team at JPL began what can only be described as a form of long-distance surgery performed blind, guided only by whatever fragments of signal they could coax out of the spacecraft. Engineers pored over documentation written in the 1970s, documentation for systems that predate the personal computer, systems built on technology so old that some of the original engineers who understood it intimately had already passed away. This is the part that rarely makes headlines. The people solving this crisis had to essentially become historians and archaeologists of their own agency's past, digging through decades-old memos and schematics to understand a machine that nobody currently working at NASA had ever been trained to build. On March 1st, 2024, the team sent a command up to Voyager, informally called a poke, a gentle nudge designed to force a specific part of the FDS to try a different sequence in its code just to see what would happen. Then came the wait. 22.5 hours for the command to arrive. 22.5 more for any response to come back. Nearly 2 full days of nothing, holding their breath across a void so large that human patience itself becomes a kind of technology. On March 3rd, something changed. A different pattern appeared in the data. Not readable yet, but different, which after months of dead-end static felt like a heartbeat. Something in that ancient, half-broken system had responded to the nudge. For 4 more days, engineers dug into that new pattern, testing it, dissecting it, trying to find structure inside what still looked to the untrained eye like meaningless digital noise. And on March 10th, they found it. Buried inside the new transmission was a full readout of the entire memory bank of the flight data. Subsystem. Every instruction, every stored value, an entire snapshot of the machine's inner workings, laid bare for the first time since the fault began. It was, in essence, Voyager 1, finally answering the question everyone on Earth had been silently asking for months. What is actually wrong with you? This is not chaos, this is strategy. Every step of that process, the archived documentation, the carefully engineered poke, the patient decoding, was a masterclass in solving an impossible problem with impossibly limited tools. No physical access, no replacement parts, no do-overs, just code, patience, and 46 years of institutional memory being called on all at once. But knowing what's broken and fixing it are two very different battles. The team compared this fresh memory readout against archived data from before the failure began, hunting for the exact discrepancy, the single corrupted piece of the puzzle responsible for turning Voyager's voice into static. And what they eventually zeroed in on was almost unbelievable in its scale, or rather, its lack of scale. A single chip. One small piece of hardware inside the FDS, responsible for storing a portion of that memory, had apparently stopped working correctly, possibly the result of being struck by a high-energy cosmic particle, an unavoidable occupational hazard for any machine spending half a century unprotected in deep space. One tiny component, smaller than a coin, had brought the entire mission to the edge of extinction. Think about what that means. Not a massive systems collapse, not some dramatic, catastrophic event. Just one microscopic flaw in one irreplaceable chip on one spacecraft that can never be physically touched again by human hands. Because there was no way to replace it, the team had to do something almost poetic in its resourcefulness. They figured out how to rewrite the affected code so that it could run without needing that damaged section of memory at all. They split the corrupted code into pieces and relocated those pieces into other parts of the FDS memory that were still functioning correctly, essentially performing a surgical workaround on a computer they could never open, could never see, and could never touch, using nothing but patiently transmitted instructions sent across a gap of light that takes almost a full day to cross in either direction. And it worked. By April of 2024, Voyager 1 began sending back usable engineering data again. Not immediately, science data. That came a little later, restored piece by piece as the team continued the meticulous process of rerouting more code around the dead chip. But the spacecraft was talking again, coherently. After nearly half a year of silence dressed up as noise, the most distant machine ever built by human hands had, through a combination of decades-old engineering knowledge and real ingenuity, essentially been resurrected from 15 billion miles away. Now here's where most people stop the story. Happy ending, crisis over, back to normal. But that's where the real tension actually begins, because this rescue didn't fix Voyager 1. It bought it time. And time, for a spacecraft built in the 1970s, is the one resource that only ever moves in one direction. According to NASA's own long-term projections, Voyager 1's power source, a radioisotope thermoelectric generator that has been quietly decaying since before its launch, loses a small but steady trickle of output every single year. It was never designed to last this long. Nobody who built it in the 1970s expected it would still be transmitting data from interstellar space in the 2020s, let alone pushing toward its 50th anniversary in 2027. To keep the spacecraft alive this long, NASA engineers have had to make a series of increasingly difficult choices, shutting down onboard instruments one by one, sacrificing entire categories of scientific measurement simply to keep enough power flowing to the systems that let Voyager 1 talk to us at all. Every year, the list of things Voyager can still do gets a little shorter. Every year, the margin for error gets a little thinner. And this is where everything changes in how we should think about this story. Voyager 1 isn't just a spacecraft anymore, it's a countdown. Every fix the team performs, including the extraordinary one in 2024, isn't a permanent solution. It's a patch, a temporary reprieve, bought at the cost of engineering time, institutional memory, and a shrinking pool of specialists who still understand code written for computers with less processing power than a modern calculator. NASA has confirmed its intention to keep funding the mission well past the 50-year mark, a quiet vote of confidence in a machine that has already outlived nearly every prediction ever made about it. But confidence isn't the same as certainty. No one, not the engineers, not the mission planners, not anyone at JPL, can say with total confidence how many more of these crises Voyager 1 can survive before one of them finally proves unfixable. What most people are not seeing is that this near failure wasn't an isolated event. It was a preview. As Voyager 1 and its twin, Voyager 2, continue drifting deeper into interstellar space, their aging systems are going to keep failing in small, unpredictable ways, and each failure will be harder to fix than the last, because the power keeps dropping, the instruments keep going dark, and the pool of engineers who actually understand 1970s spacecraft architecture keeps shrinking with every passing year. The team that solved the FDS crisis in 2024 didn't just fix a chip. They demonstrated, maybe for the last time in this mission's history, that a solution was even possible at all. And there's a deeper irony sitting underneath all of this, one worth sitting with for a moment. Voyager 1 carries the golden record, a physical disk onboard the spacecraft loaded with images, sounds, music, and greetings from Earth, intended as a message to any intelligence that might one day intercept it, sailing silently through the galaxy long after the spacecraft itself goes dark. We built a machine to carry humanity's voice into the void forever. And for nearly 5 months in 2023, that same machine could barely manage to send a coherent sentence back to the very people who built it. The most poetic messenger in human history nearly lost the ability to speak to its own creators before it ever had the chance to speak to anyone else. So where does that leave us? Right now, today, Voyager 1 is still out there, still transmitting, still the farthest flung outpost of human presence in the universe, carrying instruments that are slowly being switched off one by one to conserve the last drops of power from a battery that has been quietly dying since before most of the engineers currently monitoring it were even born. It survived a crisis that, by any reasonable measure, should have ended the mission. It came back from what looked, for months, like permanent silence. But the clock underneath all of it never stopped running, and it never will. The question nobody can answer yet is simple. And it's the same question that's been sitting underneath this entire story from the very beginning. When the next failure comes, and it will come, will there be another chip to route around, another workaround waiting to be discovered by engineers still willing to read 50-year-old documentation line by line? Or will the silence, when it finally comes again, be the kind that no clever piece of code, no patient 2-day round trip of signals, no 46 years of institutional memory can ever undo? Somewhere out past the edge of everything we can reach, a machine built before most of us were alive is still listening for our voice, still answering when it can, buying itself a little more time with every signal it manages to send home. Nobody knows how many more times it will be able to answer. Nobody knows how much longer that thin, fragile thread across 15 billion miles of empty space is going to hold. All we know is that it's still there. For now,